Good morning, good afternoon, and good evening. My name is Jeong Kim. I'm working at the Radiation Health Institute, a Korea Hydro and Nuclear Power Company, KHNP. KHNP is the only company operates all nuclear power plants in Korea. My topic is the development of physical human phantom based on 3D printing technology. About this topic, I present the recent experience to make the prototype phantom of Korean model. As you know, the computational models are widely used in various fields to estimate the effective doses to workers. Recently, with the help of advanced computing technology, radiation doses can be easily and precisely calculated by using these models. However, it has still limitations. To calculate the dose, we should input the old information about the radiation geometry. The quality of this result is only up to what new input. In most working places, we already know the radiation field, source terms, and workers' postures as planned. But in nuclear power plants, the situation is very different. Radiation fields are very complex, so we should measure and define the radiation source terms to evaluate the occupational dose before applying it to computational models and radiation simulations. However, it is almost impossible. As for the internal dose assessment, we should know how much radionuclides are inside the body. To do this, proper calibration for the measurement system is necessary. For this, radioactive calibration sources and real phantoms can be used for comparison with the mathematical simulation to match the standard geometry. There are three major 3D printing methods. First, the stereolithography SLA method is a form of a 3D printing technology used for creating models, prototypes, patterns, and production parts in layer by layer fashion using photochemical processes. Second, the fused deposition modeling, called FDM, is a technology where the melt extrusion method is used to deposit filaments of thermal flat sticks according to the specific pattern. Similar to 3D printing, the layout of FDM consists of a print head able to move along X and Y directions of our build platform. The last one is selective laser sintering. SLS is an additive manufacturing technique that uses a laser as a power source to sinter powdered material, typically nylon or polyamide, aiming the laser automatically at the points in space defined by 3D model, binding the material together to create a solid structure. In our experience, SLA is suitable for making organ parts directly, and FDM is good for modeling for application of other tissue equivalent materials. This slide shows the first Korean physical phantom model developed in 2005. In the time, we already used the 3D technology. But as you see, only three different tissue equivalent materials, soft tissues and bone and lungs, were applied. The skeleton parts are made directly by SLA method using epoxy resin. Lungs and outermost parts are made by mold using same SLA method. However, the appearance is more or less the same with the mathematical boxer phantoms. This slide shows the general procedures to make a physical phantom. Using a whole body scan images, 3D conversion to STL format to make 3D printing should be done. And move on to the direct printing or molding for selected organ with proper tissue equivalent materials. And finally, test and verification should be done. These features shows the procedures to make the long prototype. A selection of tissue equivalent materials is very important to make real physical phantom. To do this, the density and Hounsfield units by CT images should be checked. This picture shows the nominated tissue equivalent materials and tests by the CT scanning. This shows the bone equivalent materials. As you know, the bone is not the same density, so we applied 3 different types of materials to skeletal parts in a newly made phantom. And this slide shows the procedures to make a sliced phantom for organ dose evaluation for external irradiation. Compared with the previous model, various types of soft tissue equivalent materials were applied, and dosimeter holes was simplified for easy handling. For internal dosimetry phantom, many source organs should be made and located inside the body phantom. How to locate the radioactive source into the organs and organs into the body is a very important point to be considered. Empty space should be minimized. After manufacturing, verification should be done. The best way is CT scanning. Then compare with the real human CT images. A direct dose measurement can be done as standard radiation field. And finally, the results should be compared with the computational model. A physical phantom has limitation to use in various user-defined geometries, so it is necessary to make a computation model based on the real phantom for various applications. This picture shows the new prototype and its computational model. Now we are trying to make proper radioactive standard source optimized to new phantom for system calibration of internal dosimetry. Various wrong sources were tested and evaluated as shown in the slides. And it is important to apply the phantom to proper LARA design. So we have planned to use it for characterization of radiation field and major working places. And using these results, nuclear power plant workers' organ dose reconstruction will be done based on personal TLD history. Thank you for your attention.